US Physics Olympiad, year 2016, USAPHO. Final round. This round consists of two consecutive parts. Part A, which had 4 problems, and part B with 2 problems. For each part they were given 60 minutes, and the solutions for all these problems you can find in the reference of the description below this video. Problem A1. The Doppler effect for a source moving relative to a stationary observer is described by formula F equal F0 over 1 minus V over C cosine theta, where F is the frequency measured by the observer, F0 is the frequency emitted by the source, V is the speed of the source, C is the wave speed, and theta is the angle between the source velocity and the line between the source and observer. Thus theta equals 0 when the source is moving directly toward the observer, and theta equals pi when moving directly away. Sound source of a constant frequency travels at a constant velocity past an observer, and the observed frequency is plotted as a function of time. The experiment happens in room temperature R, so that the speed of sound is C equal 340 meters per second. Question A. What is the speed of the source? Question B. What is the smallest distance between the source and the observer? Problem A2. A student designs a simple integrated circuit device that has 2 inputs, VA and VB, and 2 outputs, VO and VG. The inputs are effectively connected internally to a single resistor with a effectively infinite resistance. The outputs are effectively connected internally to a perfect source of EMF E. The integrated circuit is configured so that E equal G multiplied by VA minus VB, where G is a very large number, somewhere between 10 power 7 and 10 power 9. The circuits below are chosen so that the precise value of G is unimportant. On the left is an integral schematic for the device. On the right is the symbol that is used in circuit diagrams. Question A. Consider the following circuit. R1 equal 8.2 kilo ohm and R2 equal 560 ohm. Are 2 resistors. Terminal G and the negative side of V in are connected to ground, so both are at a potential of 0 volts. Determine the ratio V out to V in. Question B. Consider the following circuit. All 4 resistors have identical resistance R. Determine V out in terms of any or all of V1, V2 and R. Question C. Consider the following circuit. The circuit has a capacitor C and a resistor R with a time constant RC equal tau. The source on the left provides variable but bounded voltage. Assume V in is a function of time. Determine V out as a function of V in and any or all of the time t and tau. Problem A3. Throughout this problem, the inertial rest frame of the rod will be referred to as the rod's frame, while the inertial frame of the cylinder will be referred to as the cylinder's frame. A rod is traveling at a constant speed of v equal 4/5 of speed of light to the right relative to a hollow cylinder. The rod passes through the cylinder and then out the other side. The left end of the rod aligns with the left end of the cylinder at time t equals 0 and the x equals 0 in the cylinder's frame, and time t0 equals 0 and the x0 equals 0 in the rod's frame. The left end of the rod aligns with the left end of the cylinder at the same time as the right end of the cylinder aligns with the right end of the cylinder in the cylinder's frame. In this reference frame, the length of the cylinder is 15 meters. For the following, sketch accurate scale diagrams of the motions of the ends of the rod and the cylinder on the graphs provided. The horizontal axis corresponds to x, the vertical axis corresponds to ct, where c is the speed of light. Both the vertical and horizontal grid lines have 5 meters spacing. Question A. Sketch the whorled lines of the left end of the rod RL and the left end of the cylinder CL, right end of the rod RR and the right end of the cylinder CR in the cylinder's frame. Question B. Do the same in the rod's frame. Question C. On both diagrams, clearly indicate the following 4 events by the letters A, B, C, and D. A. The left end of the rod is at the same point as the left end of the cylinder. B. The right end of the rod is at the same point as the right end of the cylinder. C. The left end of the rod is at the same point as the right end of the cylinder. D. The right end of the cylinder is at the same point as the left end of the cylinder. Question D. At event B, a small particle P is emitted that travels to the left at the constant speed Vp equal 4/5 of speed of light in the cylinder's frame. Question 1. Sketch the whorled line of P in the cylinder's frame. Question 2. Sketch the whorled line of P in the rod's frame. Question E. Now consider the following in the cylinder's frame. The right end of the rod stops instantaneously at event B and emits a flash of light, and the left end of the rod stops instantaneously when the light reaches it. Determine the final length of the rod after it has stopped. You can assume the rod compresses uniformly with no other deformation. Any computation that you do must be shown on a separate sheet of paper and not on the graphs. Graphical work that does not have supporting computation might not receive full credit. Here are presented 2 sheets for your diagrams. Problem A4. The flow of heat through a material can be described via the thermal conductivity K. If the 2 faces of a slab of material with the thermal conductivity K, area A and thickness D are held at temperatures differing by delta T, the thermal power P transferred through the slab is this expression. A large flat lake in the upper Midwest has a uniform depth of 5 meters of water that is covered by a uniform layer of 1 centimeter of ice. Cold air has moved into the region so that the upper surface of the ice is now maintained at a constant temperature of negative 10 degrees Celsius by the cold air. An infinitely large constant temperature heat sink. The bottom of the lake remains at a fixed 4 degrees Celsius because of contact with the Earth, an infinitely large constant temperature heat source. It is reasonable to assume that heat flow is only in the vertical direction and that there is no convective motion in the water. Question A. Determine the initial rate of change in ice thickness. Question B. Assuming the air stays at the same temperature for a long time, find the equilibrium thickness of the ice. Question C. Explain why convective motion can be ignored in the water. Some important quantities for this problem you can take from this table. Problem B1. A uniform solid spherical ball starts from rest on a loop, the loop track. It rolls without slipping along the track. However, it does not have enough speed to make it to the top of the loop. From what height h would the ball need to start in order to land at point P directly underneath the top of the loop? Express your answer in terms of r, the radius of the loop. Assume that the radius of the ball is very small compared to the radius of the loop and that there are no energy losses due to friction. Problem B2. Part A. A spherical region of space of radius r has a uniform charge density and a total charge positive q. An electron of charge negative e is free to move inside or outside the sphere under the influence of the charge density alone. For this first part, ignore radiation effects. Question 1. Consider a circular orbit for the electron where r small less than r big. Determine the period of the orbit t in terms of any of all of r small, r big, q, e, and any necessary fundamental constants. Question 2. Consider a circular orbit for the electron where small r greater than big R. Determine the period of the orbit t in terms of any or all of small r, big R, q, e, and any necessary fundamental constants. Question 3. Assume the electron starts at rest at r small equal to r. Determine the speed of the electron when it passes through the center in terms of any or all of big R, Q, E, and any necessary fundamental constants. Part B. Accelerating charges radiate. The total power P radiated by charge Q with the acceleration A is given by formula P equal C xc a power n, where c is a dimensionless numerical constant which is equal to 1 over 6 pi. C is a physical constant that is a function only of the charge q, the speed of light c, and the permittivity of free space epsilon 0, and the n is a dimensionless constant. Determine C and n. Part C. Consider the electron in the first part, except now take in account radiation. Assume that the orbit remains circular and the orbital radius small r changes by the amount absolute value for dr much less than small r. Question 1. Consider a circular orbit for the electron where small r less than big R. Determine the change in the orbital radius delta r during one orbit in terms of any or all of small r, big R, q, e, and any necessary fundamental constants. Be very specific about the sign of delta r. Question 2. Consider a circular orbit for the electron where small r greater than big R. Determine the change in the orbital radius delta r during one orbit in terms of any or all of small r, big R, q, e, and any necessary fundamental constants. Be very specific about the sign of delta r.